All right, so the last couple of days we've been talking about electron configuration. And one of the things we talked about when we talked about the electron configuration of an atom is that sometimes when you do the electron configuration, when you do it, we write the electron configuration for what we call the ground state. And then sometimes we can write an electron configuration for an excited state. So as we talked about in class, the ground state is when all of the electrons are in the lowest possible energy level, whereas when you have an excited state, it's because the electrons have been moved up, have been excited, have received energy from somewhere, and one or more electrons has been moved up to a higher energy level. And when it falls back down, it releases light. Okay, and now today what we're going to talk about is we're going to talk about just that, is that energy that is released when the electron falls back from an excited state to the ground state, about that light. So early in the 1900s, so again, quite a while ago, scientists observed that certain elements emit visible light when heated in a flame. So again, we've talked a little bit about that. When you heat something in a flame, you're adding energy to it. And when you add energy to that atom, the electrons can move up to a higher energy level. Okay, and when they looked at the color of the light that was produced, they were able to correlate this to the number of electrons in that element's atoms. So what we can do is we can look at different colors of light and different parts of light, and we can determine a lot about the electronic structure of the atom. Now, many times when we talk about the term light, we're not actually talking about light. We're talking about something that's called electromagnetic radiation. Really, another term we could use for electromagnetic radiation is light. However, if we look over here on the right side, we can see that visible light, if we zoom in here, visible light is a very, very small portion of this whole spectrum of electromagnetic radiation. Electromagnetic radiation is a very big spectrum of different types of energy, and a very, very small part right in here is the stuff that we can actually see with our eyes. So, electromagnetic radiation is a type of energy, so it's really just energy, that carries that energy through space. And again, sometimes we look around and we can see visible light, but radio waves, the way that we listen to the radio, the way that we watch television, that is a type of electromagnetic radiation. When you go to the doctor and you have to get an X-ray, that is a type of electromagnetic radiation, and there are many, many other ones as well. Lasers, ultraviolet light, gamma rays. There's lots of different types of electromagnetic radiation. Now, because again, sometimes we refer to this electromagnetic radiation as just light, it's all traveling at the speed of light, which is 3 times 10 to the 8th meters per second. And again, if we write that out as a regular number, you'll see that 3 times 10 to the 8th is 300 million meters per second. So that means, again, roughly a ray of light, if it could travel around the Earth, it would travel around the Earth about 7.5 times in 1 second. So that's a pretty fast, light travels very, very quickly. Okay, and again, all these ones here all travel because they're all electromagnetic radiation. They all travel at the speed of light because, again, they're all just different types of light. That some of it we can see and some of it we can't. So again, if we start down here at the very bottom, we can see that we've got radio waves down here, and then we've got things called microwaves, which makes you think of microwaves, I know. And then we've got infrared, which again, that's what lasers are made out of. Then ultraviolet, that's that dangerous stuff from the sun that burns our skin. We've got X-rays, and then we have gamma rays up here at the top. And again, within our spectrum here, we can see that red is at the bottom and kind of the purpley colors are at the top. And we're going to come back to that here in just a little bit. But remember that red is at the bottom here, and violet or purple is towards the top. Now, we know that all of this light here, all of this electromagnetic radiation, it all travels in waves. Okay, just like when you think of a wave out on the ocean, a wave that light travels in also is the same thing in that it looks like this, and that it goes up, it goes down, it goes up, it goes down, just like any other wave. Okay, some of the things that we measure within that is we measure what's called the wavelength. Now, the wavelength is measured in something with a Greek letter called lambda. Typically, when I write it, it kind of looks like that. It kind of looks like an upside down Y. And the wavelength is just that. It is the length of the wave. It's the distance between two repeating points on a wave measured in meters. So right here we can see this right here, the distance from here to here, the distance of one wave is called the wavelength. And then again, you can see the fancy little symbol they use for the Greek letter lambda. Okay, now radio waves tend to have very long waves. So coming back up here, these ones down here at the bottom have very, very long waves. So again, looking at red versus the purplish colors, blue and purple, okay, red have very long waves, whereas the bluish purplish colors have shorter waves. Okay, so radio waves have really long waves. We can measure them even in kilometers, whereas X-rays or gamma rays have really, really short waves, and sometimes we measure those in what are called nanometers, and the symbol for that is nm. Now, wavelength, pretty simple to understand. You look at the wave, you go, oh, okay, the distance from here to here, that's one wavelength. All right, good. Okay, then we come over to frequency, which looks like a V. Now, this one's a little bit more challenging to understand, but it is the number of complete waves that pass by a certain point each second. And what that means, it means if I was looking out here and just looking straight out, and I could see, and I can't, but if I could see the waves traveling, we know that up here on the mountain we've got the radio towers, and they're shooting radio waves down, and we can turn on the radio and we can listen to music. Well, if we could actually see those waves, I could look at them passing through this classroom right now, and I could say, oh, okay, as one passes by, I count, and I go, okay, one, and then another one passes by, and I go two, and another one passes by, and that's three. So I'm looking at one point, so it passes by a certain point. Well, what point? Whatever point I'm looking at. If I'm just counting the waves as they go by, okay, it's the number of waves that pass by every second. Okay, now the units they use for that are hertz. More commonly, though, you're going to see this, and I'll talk about what that means here in just a second. That is a second, and then there is a -1 up in the corner. Okay, now, for example, if you listen to the radio, if you listen to Power 99, it's 99.1 megahertz. Now, what that means, mega means a million. So 99.1 megahertz means that there's 99.1 million waves that pass by every second. So if I'm looking right here again, and I'm just watching the wave pass by, and I could count obviously really, really fast, Power 99, I would be able to count 99.1 million waves that would pass by that second. And that's what that seconds to the -1 means, is if you write 25 hertz, that's the same thing as writing 25. And really what that means is 25s, and even though we don't write it, it means that 25 waves pass by every 1 second. Now, obviously, that's a very low frequency compared to something like a radio station that has 99.1 million. But remember, how fast are these waves traveling? They're traveling at the speed of light very, very quickly. So when we say 99.1 million, that's actually a really, really big wave. That's a radio wave. And remember, we said that radio waves have really, really long waves. And so as that wave goes by, again, every second, there's 99.1 million of them. Okay, now over here, it does talk a little bit about amplitude along with wavelength. That isn't something that we're going to measure. You can see that amplitude is just how high the wave is. But again, in terms of wavelength and frequency, we're not too worried about it. We do know, again, coming back up here, that the lower you are on this spectrum, the longer the waves are. And you can probably see it over here. That here you can see 1 kilometer, 1 meter, but then as you go up, they do get shorter and shorter. This is called a micrometer. And so as you move up the scale, the waves do get shorter and shorter. So again, in terms for us in our visible spectrum here's our visible spectrum again. The red, orange, yellow, those are the longer waves. The blue, purplish colors, those are the shorter waves. Okay, now what we can do is we can do something here with our wavelength and our frequency, and we're going to make an equation with that. So what we're going to do is we're going to relate the 3 things that we've talked about. We've talked about the speed of light, we've talked about frequency, and we've talked about wavelength. So here, right here, that letter C, okay, is equal to the speed of light. Just like in that, there's that famous Einstein equation, E equals mc squared. That C in E equals mc squared is this same C. It is the speed of light. Now, the nice thing is it's a constant. It is always 3.00 times 10 to the 8th meters per second. So the speed of light never, ever changes. Okay, and then we have our frequency and we have our wavelength. Okay, and we can see that frequency times the wavelength is equal to the speed of light. So just like with the density equation, we can make a little triangle. If you put C up on the top, if you want to find wavelength, you just cross out wavelength. Wavelength is the speed of light over the frequency. Okay, if you want to find the frequency, you cross that out, and it's the speed of light over the wavelength. So there's always a way that you can find any of those. So if you know one thing, you can find the other thing. Now, you'll notice here, if the speed of light never changes, if the wavelength is big, what does that tell you about the frequency? Well, again, if the speed of light doesn't change, if the wavelength is big, then the frequency is small. Okay, and vice versa. If the frequency is big, what's the wavelength going to be? The wavelength, therefore, has to be small. So there is that relationship between them, that if one is big, the other one is smaller, and vice versa. So here's a couple of example problems we can do here. It says, calculate the frequency of a wave that has a wavelength of 2,500 meters. So we want to get the frequency of the wave. So first of all, let's think about what that means. Frequency, again, coming back over here, is that lowercase v. Okay, and we want to solve for that. So they want us to calculate the frequency. So to get v by itself, I'm going to take the speed of light over the wavelength. So again, the speed of light never changes. So that's going to be 3.00 times 10 to the 8th meters per second. The wavelength, it says, is 2,500 meters. Okay, and you'll notice I've got meters on top, I've got meters on the bottom. Notice that this is meters over seconds. So really I should be writing that like this, meters over seconds. So now I'm going to take 3 times 10 to the 8th, and I'm going to divide by 2,500. And just because there's a bunch of zeros there, I'm going to put it in scientific notation. 1.2 times 10 to the 5th. And notice my seconds are on the bottom, so that becomes seconds to the minus 1. So that means that if a wave has a wavelength of 2,500 meters, its frequency is going to be roughly, not roughly, it should be exactly, if I put it back into a regular number, into a decimal form, it's 120,000. So that means 120,000 waves will pass by every second. Okay, the second example says calculate the wavelength of a wave that has a frequency of 2.56 times 10 to the 19th. So now let's come back over here. So in this case, they want the wavelength. So let's get rid of that. So it's speed of light over the frequency. So wavelength equals speed of light over the frequency. And the speed of light, again, never changes. 3 times 10 to the 8th. Notice how I write it this time, meters over seconds. and then I'm going to put my 2.56 times 10 to the negative 19th, and that's seconds to the minus 1, which really means over seconds, so we're going to see those seconds do cancel. So now I'm going to take 3 times 10 to the 8th divided by 2.56 times 10 to the negative 19th, and I get 1.17 times 10 to the 27th. And again, all I have left is meters. Now that's a huge wave. You know why? Because I screwed up. Dang it. That's not 10 to the negative 19th there. It's 10 to the 19th. So clearly I made a mistake there. And that's okay. But notice that when I got done, I thought, wait a minute, that's such a big number. It can't be that big. And then I went back and I looked and I went, oh no, I put that negative in there when it's not supposed to be negative. So let's try this again. Let's get rid of that negative there. 3 times 10 to the 8th divided by 2.56 times 10 to the regular 19th. And obviously that changes our number drastically to 1.17 times 10 to the negative 11th meters. How about that? Is that better? Okay, so now we have now we went from a really big wavelength to a really small wavelength. Okay, and again, when I thought, as soon as I realized my mistake, I thought, wait a minute, a frequency of 2.56 times 10 to the negative 19th, that seems a little bit too small, because that means there's less than one wave passing by per second, and it's traveling at the speed of light. That'd have to be a huge wave. So clearly, usually this number for frequency is a fairly large number. Okay, now how does that relate back to, again, that idea of you have an electron that's in the 3s subshell, and that electron, when it gets excited, remember, it goes up to a higher energy level. Maybe it goes up to the 6s subshell, but then once it gets there, that's too far away, it's unstable, it's reached its highest energy point, and now, like a rope swing, you've reached the highest point in the rope swing, and now you have to come back down. Well, now it's going to come back down, and when it does, it comes back down to the 3s, and when that happens, it releases energy. And that energy that it releases, again, many times, if it's within that spectrum, that visible spectrum, then we can see a color. If it's not, then obviously we can't, but it would have to be within that. Now, how much energy gets released comes back to this equation right here. It has to do with the frequency. Okay, the energy of a single photon, and we'll talk about what that means here in just a second. So the energy is equal to, so the energy, capital E, is equal to something called, this is actually called Planck's constant. A German physicist named Max Planck came up with this equation, and so they named this constant after him. So this is kind of like the speed of light, and that is it is a constant. It never ever changes. And so since it doesn't change, it means it's always going to be that same number, and it's always this number right here. So H, just like C is always 3.00 times 10 to the 8th meters per second, H is always this 6.63 times 10 to the negative 34th. And again, H is a constant, and it always is equal to that number. So the energy is equal to this Planck's constant times the frequency. Wait, is that same frequency from up here? Yes, it absolutely is. And that's how you can go between those two equations, is if you have the wavelength, you can get the frequency, and then you can use the frequency to find the energy. So the energy of a single photon, let's talk about what that means. Because this number right here, clearly a negative 34th, that's a really small number. And even though frequency is usually a big number, your energy usually always comes out to be also a very small number, simply based on that value of H right there. Now, the reason that is because energy, light, as it travels in these little tiny packets of energy. So when we look, when we see light, we don't actually notice the waves. We don't see the up and the down, and we don't see the little packets of energy that it uses. But absolutely, when light travels, it travels in these little, kind of like a train car. When that train car gets filled up, it goes to the next train car. And every single train car is made up of energy. And again, we obviously don't call it a train car, we call it a photon. And so every wave has these little tiny packets of energy called photons. And that's what that energy is. It's the amount of energy in just one photon. So again, it's going to be really, really small because energy is also very, very small because we're talking about such a small amount of energy there. Now, let's just kind of think, coming back here to our electromagnetic spectrum, is that we said that red and orange tend to have longer waves and the bluish purplish colors have short waves. Well, the longer the wavelength, let's come back over here to our equation down here. The longer the wavelength, what can we say about the frequency? Remember, speed of light is constant. So the longer the wavelength, the smaller or the shorter the frequency. So longer waves means shorter frequency. And therefore, the shorter the wave, the longer, or the larger, however you want to say it, the larger or longer the frequency. Okay, or even greater than less than. A long wave produces a frequency that is smaller, shorter, again, however you want to think about it is fine. Now, using this equation here, the energy equation, we know that, again, this is constant. So we know that the smaller the frequency, therefore, the smaller the energy. And the greater the frequency, the greater the energy. So smaller frequency, so let's come back here then to this one right here. The shorter the frequency, the lower the energy. So all of those are all tied in together. That red light has a lower energy than bluish purplish light because the shorter the waves, the longer the frequency or larger the frequency, and then the greater the frequency is, this is going to have a higher energy. So red is a low energy light, whereas purple and blue are high energy lights. All right, so let's take a look here at a couple of examples. So the first one says, calculate the amount of energy in a wave that has a frequency of 2.96 times 10 to the 23rd hertz. Now, when I see hertz, to make it easier on myself, I just write seconds to the -1, and then when it cancels, it makes it a lot easier. So calculate the amount of energy in a wave. It really should say not in a wave. It should say in a photon that has a frequency of that number. So we know that energy is equal to Planck's constant times the frequency. So Planck's constant again is 6.63 times 10 to the -34th. And that's J. And that we haven't talked about that. That stands for joules. And joules is just a way to measure energy. It's a unit, kind of like when for us we use calories. Calories, think of, well, I have to eat only 2,000 calories a day or whatever. Okay, that's a unit of energy. That's how much energy that food has. And if you don't use it, then your body stores it for you. Well, another unit of energy, like calories, is something called joules, Joules. And that is in the metric system. So you can have kilojoules, you can have millijoules, just like you can have kilometers or kilograms and milligrams and stuff like that. So joules, and then we have an S, and that is the seconds part. And now we're going to multiply that because it's Planck's constant times the frequency times 2.96 times 10 to the 23rd, And again, that's a seconds to the minus 1. And so really, remember, that means that number is over seconds. So those seconds and those seconds cancel. And so now I need my calculator. 6.63 times 10 to the negative 34th times 2.96 times 10 to the 23rd gives me a value of 1.96 times 10 to the negative 10th. And everything's gone except for joules. Now, again, you might look at it, wow, that's a really, really small number. Remember, that's one little photon. And sometimes you'll even see it written like that, joules per photon. You don't have to write that, but that's just a good way to help you remember what that actually means. That's the amount of energy that one little photon of light has. And again, that's always going to be a pretty small number there. Okay, last one. Calculate the frequency and the wavelength of a wave that has an energy of 8.42 times 10 to the negative 18th joules. So here's one where when we look at our equation here, they're giving us the energy. And they're giving, we always know Planck's constant. So here we're trying to find the frequency. So we can see that it is just energy over Planck's constant. So that's our first thing we're going to do is we're going to calculate the frequency. So frequency is going to equal E over H, just like our equation shows us. And it tells us that the energy is 8.42 times 10 to the negative 18th joules. And Planck's constant, again, is always 6.63 times 10 to the negative 34th joules seconds. Our joules cancel. And notice we have seconds left on the bottom, which again, that's what frequency is. So 8.42 times 10 to the negative 18th divided by 6.634 times 10 to the negative 34th gives me a, and again, frequency is usually a big number because remember, it's the number of waves that pass by every second. Well, again, that's always a lot when things are traveling at the speed of light. So 1.27 times 10 to the 16th seconds to the minus 1. And that gives us our frequency. So we've done the first part. We've calculated the frequency. And now they want the wavelength. So remember our equation with wavelength is the speed of light is equal to frequency times wavelength here. And so in this case, they want us to find the wavelength. So let's get rid of that. So it's the speed of light over the frequency. So wavelength is equal to the speed of light over the frequency. So 3 times 10 to the 8th meters over seconds is the speed of light, divided by 1.27 times 10 to the 16th seconds to the minus 1. Those are going to cancel. So 3 times 10 to the 8th divided by that last answer that was just on my screen to make it easier so I don't have to push in as many buttons gives me an answer of 2.36 times 10 to the negative 8th. If your calculator just did 0.000000 and then a whole bunch of zeros and a 2, put it in scientific notation. So remember, on some of them, on mine, I hit second, and then I hit the SCI button right here, and that puts it back, puts it into scientific notation for me. But if your calculator does just 0.00, just a whole bunch of zeros, and then a 2, it means it's going to show a lot more if you put it into scientific notation. So that's where I came up with that number there.